The last example we are going to do is a circle doubling map. Remember, this is a map denoted by T2, goes from T to T, sending a point here to twice of that, mod 1. And then in the book, this is from the example 2.4 in the first section. And the proposition says that this circle doubling map is ergodic. Again, with respect to the Lebesgue measure. Do you see why this is true? This should be immediate to you if you remember one of the examples we did before. Remember, by the example 2.8, we have the following two isomorphic measure preserving systems. One is this circle doubling map. Remember, this is on the space T, equipped with the Lebesgue measure with this transformation circle doubling map. And the other one is, do you remember? It is the so-called Bernoulli shift. The space is this infinite product space, and the measure is the infinite product measure. Mu sub half-half, and the transformation is sigma. So sigma is the Bernoulli shift, shifting an infinite sequence to the left by 1. They're isomorphic. Now, by the proposition 2.15 above, the latter, namely this guy, is ergodic. Actually, what we proved in the proposition 2.15 is a case that is more general and slightly different. So in there we have instead of non-negative integers, we have the full integers z here, and but the shift is still the shift to the left by 1. The difference is that back in the proposition 2.15, you get a two-sided infinite sequence. But the proof in there should apply to this case without any essential changes. So you can easily see from the proof in there that this guy is still ergodic, because they are isomorphic and because the latter one is ergodic. So you can guess that the first one has to be ergodic as well. And to be more rigorous, let's still try to prove this, that if you are if you have two measure preserving systems that are isomorphic and one of them is ergodic, then the other one is also ergodic. First, let's move the definition of isomorphism here. The key part is that you have the community diagram here, and this vertical map is invertible. And now, every map involved in this diagram is measure preserving. Now, suppose the system in the above is measure preserving. Suppose the system above is ergodic. So if x, bx, mu t is ergodic. Now for any b in b sub y, we want to show that the nu of b, remember nu is a measure on y, is either 0 or 1, which implies that we want to show that for any b in b sub y, such that b is invariant under S, we have nu of b is either 0 or 1. Remember, nu is a measure on y. Okay, to show this, you simply do it straightforwardly. You start with nu of b, and because phi is measure preserving, you have this guy is equal to mu of phi inverse of b. And this, we claim, is either 0 or 1. The key part in here is that first, you're going to use that the measure mu is ergodic under T. And second, you need to prove that T inverse of phi inverse B is equal to phi inverse of B. To prove this, you're going to use this commutative diagram. So let's check quickly. T inverse applied to phi inverse B is equal to phi composite T inverse applied to B. And this is equal to S composite phi inverse applied to B by the commutative diagram. So phi composite T is equal to S composite phi. And this is equal to the phi inverse composed with S inverse applied to B. Because B is assumed to be invariant under S, so we are going to get phi inverse of B in the end. So this shows the phi inverse of B is invariant under T. And this finally shows that nu of B is either 0 or 1. So finally we proved that this circle W map is ergodic. That finishes this proposition as well as this section 2.3.